We have seen astronauts in the International Space Station in a state of weightlessness, right? They don't experience their weight. They don't experience rather gravity, right? And that the reason is, the reason most of us think is that in space there is no gravity, right? There's no gravity, so they don't experience any. Their weight is zero. Is that the case? Number one. And number two, how can we, if we were to replicate that state of weightlessness within the Earth's gravity or within the Earth's atmosphere, is there a way to do it? Can we have a zero gravity region in the Earth's atmosphere? So in this video we will explore that. So first we will understand how the astronauts in the International Space Station, they are in a state of weightlessness, and then we will extend that understanding to explore whether that sort of environment can be replicated in the Earth's atmosphere. So let's say this is the Earth, and let's say this is the International Space Station, and in that there is this astronaut, and this space station is moving in a circular direction around the Earth. So let's take this the space station and the astronauts inside the space station as the system. So the system as a whole is moving in a circular direction, or rather rotating about the center of the Earth. So what is the force which is being experienced by this system of the International Space Station and the astronauts? So that will be the force of gravity due to the Earth, because the fact that the space station is rotating about Earth, that is because of the gravity of the Earth, right? If there were no gravity, then the space station would not rotate, right? Earth rotates around the sun. Why? Because of the gravity of the sun, right? The same way the space station is like a satellite, and it rotates about Earth because of the gravity of the Earth. So, and apart from gravity, there is no other major force, at least known force, on this space station. So given that this space station is moving in a circular direction, so definitely the space station and the astronaut system will have centripetal acceleration, assuming that we are not in the frame of reference of the space station, we are in the frame of reference of Earth, let's say. And let's assume that the speed of the space station is constant. In this circular motion is constant. The velocity will change, of course, because in circular motion velocity will change, the direction of velocity will change, but let's say the speed is constant, so the tangential acceleration is not there. So if we apply the normal Newton's second law equation on this circular motion, then what do we get? This external force which acts on the space station, which is the gravity, force of gravity, that will be equal to the centripetal force. So what is the so let's say the mass of the space station and the astronaut is m dash. So what is the force of gravity on this system? It will be g, gravitational constant, into mass of Earth into m dash divided by r square, where r is the distance of the space station from the center of Earth, and this is the centripetal force, which will be what? M mass, like the mass of the space station, times the centripetal acceleration. So what is the centripetal acceleration? The centripetal acceleration is g capital M by r square. So this is an important concept. Now the space station and the astronaut system is having when it's moving in a circular direction, so this system is having a centripetal acceleration of g capital M by small r square. Now we can say that even the astronauts who are inside the space station, they are also rotating in a circular, moving in the circular path, right? So they will also have the same centripetal acceleration, which will be g capital M by r square. So this is important. Now let's try to understand why the astronauts in the space station are in a state of weightlessness. Like, do they experience zero gravity? Not right, not really, right? Because we have seen that the space station and this astronaut system do experience the force of gravity. Then why the astronauts are in a state of weightlessness? Of course, the force would be less than what they would experience on the surface of the Earth, because it's inversely proportional to the square of distance. But still, they do experience some gravity. But why are they in a state of weightlessness, which is zero gravity? So let's now take the one astronaut as our system, not the space station, but the astronaut inside the space station as our system. So if we take one astronaut as the system, then as we discussed that this astronaut is also moving in a circular direction. So let's draw the free body diagram. So let's assume that the mass of the astronaut is m. So what are the other forces acting on the astronaut? So the first force would be the gravity on the due to the Earth on the astronaut, which will be Fg, let's call it Fg, and that will be towards the center of the Earth. and the other force would be the normal reaction because of the space station. So let's say this astronaut is resting on the space station or standing on the space station. So because the space station, we know that I mean, any surface, if you are on a surface, then the surface will exert a normal reaction. So that's the normal Newton's law. So this surface will experience will exert a normal reaction. So then, so the net force on this astronaut is what? Fg plus n, and given the astronaut is moving in a circular direction with this, and so it's having a centripetal acceleration. So this net force is equal to the centripetal force. So we'll put the values. So let's say the mass of the astronaut is m. So when you put the values here, this we find that you see this equation. We find that the normal reaction is equal to 0, right? So I mean, when the astronaut is inside the space station, which is moving in a circular direction, or which is rotating about the center of the earth, and there is only force of gravity on the space station or on the astronaut, then we find that the astronaut inside the space station does not experience any normal reaction. So if we do not experience any normal reaction from the surface, it means what? It means that our apparent weight is 0, right? And that's why the surface is not exerting any force. So that's the state of weightlessness, right? So for the state of weightlessness to be there has to be two conditions, right? First condition is that the frame of reference in which you are, that frame of reference should be, we're trying to summarize and draw some analogy from this astronaut and space station example. So if we draw some analogy from that example, then for an object to be in a state, for an object to be in a state of weightlessness, the frame of reference in which the object is there, that object should be in a circular motion, and the only external force on that on the object or the frame of reference should be the force due to gravity. So if these two conditions are fulfilled, then we can have a state of weightlessness, as we are seeing in this astronaut and ISS, International Space Station example. So now, having seen this and having observed this, is there a way we can replicate this sort of scenario in the Earth's atmosphere, not in outside space, but in the Earth's atmosphere? So those two conditions, right? A moving frame of reference in circular direction and having gravity only as the external force. So can these two conditions be replicated inside the Earth's atmosphere? If we can do that, then we can have a state of weightlessness. Now let's see how can that be replicated inside the Earth's atmosphere. Now those two set of conditions can be replicated inside the Earth's atmosphere in a specific region, right? Which we will see now. So let's say this is Earth, right? Let's say this is Earth, and you have an airplane, right? And an airplane is normally when we travel in an airplane, so the airplane of course moves from point A to point B on the Earth. But on a normal airplane, we do not experience any state of weightlessness. But if a normal aeroplane, or if any aeroplane is made to follow a particular trajectory, then within a section of the trajectory, a state of weightlessness can be experienced. Or in other words, within a section of the trajectory, those two conditions which we discussed, like the frame of reference moving in circular direction and and only external force being that of gravity, so those two conditions can be fulfilled. So we will see what that trajectory is. So let's say you see this plane is there, right? And let's say this is position 1 of the plane, this is position 2 of the plane, and this is position 3 of the plane. This is the normal motion of any plane. In this section, you see that the plane is having an upward ascent, right? The plane is kind of moving upward at a particular angle from the horizontal. And here, here in this region, which is region A and 2B, in this region we see that the plane is having a near about circular motion, right? It's not completely circular motion, but yeah, this is kind of a circular motion. So when the plane follows this trajectory, then basically in this part, which is this AB arc, in that region, those two conditions get fulfilled. And let's see how. So basically in this part AB, given that those two conditions fulfilled, we can experience a state of weightlessness. And there are planes, and this has been established. It's not a new concept. There are zero gravity planes which follow the same principle, which follow the same trajectory, and in this in this small region, small arc, people who are inside the plane, they experience that state of weightlessness. So let's understand this arc, this trajectory in more detail, and why in this arc that those two conditions get fulfilled. So now let's consider state 1. So in this state 1, when the plane is moving normally, what are the forces which is acting on the plane? The forces which is acting on the plane will be what? There will be a gravity, right? There will be the thrust because of the engine of the plane, which will be, let's say, in this direction, and the plane, and there, because of the Earth's atmosphere, there will be drag on the plane, right? And the drag would be in the opposite direction. So you see right here, there are three forces, right? So those conditions are not, do not hold true, because there is not only gravity, there are other forces also. So now let's say here the plane starts to move upward, right? The plane starts to ascend, and let's say it ascends at an angle, some angle theta. So now in this state, will you have that state of weightlessness? In this state too, again, the motion is not circular. The motion is like a like a straight line, like a slope of an incline. That's the motion. And number two, what are the forces on the plane? The forces are, this is again due to gravity, and then there will be this thrust because of the engine of the plane, and there will be the air drag, right? So again, in this state 2 also, there will not be like the weightlessness will not be there, because both the conditions are not getting fulfilled. Now let's say if the thrust of the while the plane is moving up, if the thrust of the engine is adjusted or reduced to an extent that the thrust of the engine is equal to the drag because of the external air or atmosphere, then what will happen? Then what will be the only external force which will be acting on the plane? That will be gravity, because the thrust and the drag will cancel each other. So while the plane is moving up, if the pilot, or if you are able to reduce the the force on the plane such that the the net thrust is equal to the drag, then and let's say you are able to achieve that at this point A, right? Then from point A to point B, the only external force which will be there on the plane would be the gravity, the force of gravity on the plane, and there will not be net thrust. So because of that, the motion of the plane would be kind of a circular motion, right? Because the thrust will not be there, right? So the motion of the plane would be of a circular motion, and the speed of the plane would be more or less constant. So the tangential acceleration will not be there. So in this part A to B, the only acceleration which will be there will be kind of that centripetal acceleration, and this force of gravity will be centripetal force. In this region A to B, both those conditions which we saw in the space station for the astronaut, that is getting fulfilled. So there's only gravity, and the motion is also circular. So the plane moves in a circular direction, like it has a circular motion. So in this region, you do experience that state of weightlessness. Beyond point B, again, like the plane will move, extend its motion. So again, the motion will not be circular. So the motion will be little bit will be as if the plane is moving down a slope. So beyond point B, again you will start experiencing gravity again, right? So this special trajectory, in a particular section of the special trajectory, you will be able to experience that state of weightlessness, right? Now it has been observed that special trajectory is obtained when this angle of ascent, this theta, is equal to 45 degree, and it has been done. So in fact, in the movie Apollo 13, like some of the scenes where they depicted weightlessness and all. So those scenes were shot in a plane which had to move, which was made to move in this particular trajectory, and in a section of the trajectory, that state of weightlessness was created, and the movie was shot. And you see, right, and this particular pattern can be repeated. So you can keep on having this trajectory, right? So like once, let's say, this trajectory is over, the plane can come below, again the plane can move up, and here in this region, again the plane will have that state of weightlessness, again the plane can come down, and again that can be repeated. So yeah, that's how you achieve a state of weightlessness, or so-called zero gravity, within the Earth's atmosphere. So thank you, hope you found the video useful.